Hey students. So today we're going to talk about periodic trends. Now that we have a pretty good understanding about energy levels, or we can say shells of electrons, and the sublevels, the subshells that fit in these energy levels, now we can approach atomic size and further our understanding of basic periodic trends. So how does atomic size work? Electron shells are like layers of electrons around the nucleus. So if I have a nucleus in the center, the first electron shell or energy level would orbit that nucleus. The second would have to be outside that first orbit and be further out. The third would be even further out, and the fourth would be further out from that, and so on. So we see as we have more shells, the radius of the atom gets larger. More electron shells, bigger atom. Sublevels, so the S, the P, the D, and the F that fit in these energy levels or these shells, don't really add any thickness to the shell because they're fitting inside of vacant space. Again, those sublevels, these orbitals that we discussed, are just probability maps, so empty space that the electrons are occupying. So when we look at the main group of elements and atomic size, we see some basic trends. The first one is the easiest. As you go down a family or a group, it's easy to understand because we have more periods and atomic size increases. So the atomic size increases as you go down. So if I pick the noble gases, group 18 or 8A, as I go down, I can clearly see that helium is much smaller than radon. Why is that? Well, helium only has one energy level or one shell of electrons. We see that radon has 6. So its radius is much further out. Its valence shell is farther away from the nucleus. So as a result, it's a bigger atom. The second trend is a little bit trickier, and it's typically as we read from left to right on a periodic table, or you can think of it as going across. As you go across, you're pretty much in the same shell, the same energy level. The difference is in your nucleus, you have more protons pulling on that energy level. You can think of it as a greater effective nuclear charge. Remember, it's the protons that have positive charges, and they're pulling on the electrons, which are negatively charged, because they're attracted. So as I go from left to right, I have a greater number of protons. So here's a quick check. List the following atoms: magnesium, silicon, sulfur, and potassium in a sequence of steadily increasing size from smallest, so we want the smallest, to the largest atom. So again, this is for the periodic trend of atomic size, and this is what we want. So how do we do that? So we already said as we go down, things get bigger. So as we go down a group, things get bigger. As we go from left to right, things get smaller. So if we think in this term, this upper right-hand corner has the smallest atoms. This lower left-hand corner would have the biggest atoms. So when you think of it in terms of that, the one element that's closest to helium would be the smallest out of these 4. So if I look, sulfur is the closest to helium. It's in the 3rd energy level, and it's got an atomic number of 16. So sulfur is the smallest. Now, if I look at silicon, it's also in period 3, but it only has an atomic number of 14. So it has fewer protons pulling on that third shell. So it's a little bit bigger. If I keep going across, right? If I keep going across, I'll get to magnesium. And magnesium's also in that third shell, but it only has 12 protons pulling on it. So it's slightly larger. And the largest of them all is the potassium. Why? It actually has 4 energy levels or 4 shells. So it has the biggest radius. It also makes sense because potassium is closest to this lower left-hand corner of the periodic table. So I hope that makes sense. We'll see that using periodic trends can really help us predict other concepts as well. If you have any questions, go ahead and leave them in the comments. Thanks.